So last time we started with open channel flow and we talked about waves and hydraulic jumps. This time we're going to do what we did for pipe flow, only for open channel flow. So we're going to find velocities and flow rates and head losses and that sort of thing. So let's review. If you remember back in pipe flow, we were able to handle non-circular cross sections, and to do that what we did was use the hydraulic diameter. We're going to use that again, and hydraulic diameter, if you recall, was 4A over P. And A was the cross section of your fluid, and P was the wetted perimeter. And the wetted perimeter was where the fluid touches the walls. This is the fluid of interest, not air typically. Okay, so, but unlike the pipe flow, we're not going to directly use the hydraulic diameter. What we're going to usually use is the hydraulic radius. And for whatever reason, the hydraulic radius is not defined as dH over 2, but dH over 4, probably because of that 4 in your hydraulic diameter equation. So this becomes a very simple equation, just A over P. Okay, so when we do our Reynolds number, I don't know if you remember, but a Reynolds number had a characteristic length in it that length depended on the situation. So in this situation, we're going to define our Reynolds number as having an RH, a hydraulic radius in it. So our Reynolds number is going to be our velocity times our RH rather than a D over nu. Or if you want to write it in the longer way, rho V RH over mu. So there is a critical Reynolds number, just like there is for pipes, for open channel flow, and that is approximately 10 to the 5th. So 1 times 10 to the 5th is your critical Reynolds number, not 2300, but 1 times 10 to the 5th. Most open channel flows are actually fully rough, turbulent, very turbulent. And that's because most of your open channel flows are big flows, right? Big drainage ditches or rivers or what have you. So big means turbulent, okay? Fast means turbulent. Sometimes you can have thin sheets of rainwater that might be laminar, but usually we're talking turbulent. All right. So in open channel flow, again, we might be talking about rivers or just any kind of old drainage ditch or whatever. It could be very complicated, changing in shapes and sizes. So velocities in that case would be 3D, unsteady, and not fully developed. If you remember, fully developed meant that it wasn't changing in the x direction along the flow. So a lot of times if you're talking about a river, none of these things are it's not 1D, it's not steady state, it's not fully developed. So when we're talking about these complicated flows, it gets very, very complicated. So we can use CFD sometimes, or if we're just trying to get rough approximations, we will use a 1D approximation. Or if it's possible, maybe we do have a very simple canal or something with a simple cross section, and we can assume that we don't have 3D, unsteady, unfully developed. So as an example, we might have an open channel flow, say, driven by gravity. Maybe it's a river. Maybe the velocity profile at one spot is something like this. Maybe its cross section actually looks something like, oops. this? Who knows? What we're going to do, instead of do our real velocity profile, is approximate something like that, for simplicity's sake, as a uniform 1D velocity. Same velocity, that's supposed to be a rectangle, same velocity all the way across. Kind of ignore the no slip condition, or assume the boundary layer is very small. And the other thing we're going to do here is assume we have fully developed, which again means the velocity is not changing as we go along the x, and constant cross section. If we get a little bit more advanced, we could alternatively allow the velocity to change and the area to change. In either case, then velocity or flow rate would still be velocity times area, but it'd be velocity as a function of x times area as a function of x. And that would still be constant, but a little more complicated. So what we're going to do is we're not going to do that. This is too complicated for this class. Instead, what we're going to do is stick with uniform flow, and with uniform flow we can do these Chezy-Manning approximations. Okay, so before we do that, let's just set up our coordinate system. So our channels, our rivers, and so forth, most of our open channel flow is driven by gravity. So we're going to have a slope. What we're going to typically do is make our x-axis horizontal, not along the flow. You could call this the z-axis. And then y is going to be the depth. We've already used y as the depth. That's what we're going to do. It's also going to be the vertical depth. It's a vertical depth. If we actually want the normal depth, y, we're going to call that yn, normal to the bottom. That's the normal depth. Okay, our cross section doesn't have to be square or rectangular. It could look like this, and that's okay, as long as we can calculate our hydraulic radius. Okay, so let's think about some things right here before we go on and do some quiz questions. Just by thinking about what's going on in open channel flow, think about what parameters you think will affect the velocity in this situation. So I'm not going to write answers here. We're going to come back to these, but see if you can come up with some answers before we go on, just based on common sense.